Welcome to Deep Learning the Essentials. A little bit about myself. So my name is Liad Youssef. I'm the client architect at a company called Duda, and I'm a web enthusiast, and I'm actually a graduate of the wide data program. In my spare time, I am also an analog astronaut for the Austrian Space Forum, and I try to combine those two passions of mine of computers and space. And I'm also lecturing in the International Space University about using AI and computer vision to assist with satellite imagery. So if we combine everything together, then we'll turn from deep learning the essentials to something that's called machine learning above and beyond. And just some words about why is it important? Why is it important for us to learn machine learning? Well, especially today, especially in those times, we can harness the power of algorithms, the power of models, the power of computers. Here we can see, for example, something really quick, really easy to build that's taking a video and checks if the people are distant from each other, if they maintain social distancing, or something to recognize faces with masks. And this entire COVID situation opened up a lot of possibilities and challenges that we can use machine learning and AI to tackle. If we talk about AI for a second, so Andrew Ng speaks of AI as the new electricity, and that's really important. That's a really important thing to understand, that right now you need to know machine learning, even today, and in 5 years, every company, everyone needs to know machine learning, needs to know AI, needs to have some sort of those capabilities in-house. If we look at NVIDIA's stock, which manufactures GPUs, which are like the hardware for AI or deep learning today, we can see how it soared throughout the years. So in this talk, we're going to start from the basics. I like this quote by Abraham Lincoln: if I had 8 hours to chop down a tree, I'd spend 6 sharpening my axe, meaning we want to sharpen the skills, we want to sharpen the basics. And let's start with the intro to learning. Okay, so let's imagine this scenario. You're stranded in space. Your ship blew up and you need to get home. And all of a sudden you see a flash of light and you see a taxi that wants to take you home. And this taxi driver, he doesn't know how much to charge. So he asks you, how much do you want to pay? How much do you want to pay to go home? But you don't really know what's the cost of a taxi ride back in space. You know that it's some sort of combination of the distance you want to travel and the time that it takes to travel it. So you know it's called a linear combination. You need to multiply it with some sort of coefficient, but you don't know these coefficients. So you're starting to think, okay, you have this neuron or this friend that actually receives those two values, the distance and the time, and outputs a price, and you need to train it somehow. You need to let it know what those coefficients are. So those are called the features, and those will be called the weights. So how much do you need to multiply the features? And then you have the single neuron that should output the target. Okay, so how would you do that? Using machine learning. And machine learning, if we highlight only the important parts, is to learn the weights of the real world. So take the real world and try to understand how to learn it. So how do you do it? You get some data, right? Everybody knows that. And let's say, for example, you know the data of the last 3 rides that the taxi gave. So you call it the train data. And let's say you know that for a distance of 15 and the time of 3, the price is 125, and so on and so forth. So you take this train data and you start to input it into your neuron. So you say, okay, the featured distance when it's 15 and the time is 3, just calculate what the price would be. And the neuron doesn't know how to do that, so it just outputs random weights, right? And they can be negative or even a fraction. And then, for example, let's say you get 195. But you know that the real target, the real value is 125. So you're way off. You're way off. And the difference between 195 and 125, it's what we call, like generally speaking, the loss or the loss function, or how do we measure what is the difference of how far are we from what we wanted to measure. So we take this and we tell the neuron, okay, your weights are way too big. So we need to update them to be a little bit smaller. And then we input the next set of data. and then the neuron outputs the price according to the updated weights. And let's say now the price is too low. So we need to update the weights again. And we do it iteratively over and over and over until eventually we would get the coefficients, let's say 6 and 10, we would get those coefficients that gives us like the closest thing that we wanted for a price. And if you run it on the data, on the training data, we see that we predict a price that it's not so different from the actual price, right? Meaning that we were able to actually learn the coefficients of the real world. So that's really nice. So basically that's what we do when we train a model. We get the data, we guess the weights initially, we calculate the result, we calculate the loss, which is comparing to the target how far are we from the result, we update the weights and we repeat, and we do it over and over and over, and that's what's called training the model. So when we finish with it, the model is trained, and now we can take it and try to predict on a new data. In our situation, let's say we know that the distance is 20 and the time that it will take us to go there is 8. And I don't know, we multiply it and we get a lot of cookies, and we say, okay, no, that's way too much, it's too expensive, I can't afford it. And then you sit here and you think, okay, that's what it is. Everything is just a glorified calculator. That's all that it is. And well, basically, yes and no, because the idea, well, machine learning is not new. Yeah, the concept is not new. It's not something that we needed supercomputers to learn or to practice. But the universe is much more complicated than you think. Meaning, we have a lot of problems that it's not that easy to use linear regression, or what we saw here, or algorithmic regression. It's not that easy to use that in order to model the functions of the real world. For example, we have a problem of classification. Classification is what is it? What I'm seeing in the picture, what it is. And here we can see some examples from ImageNet. You can see, for example, a container ship is identified pretty well as a container ship, but for example, a mushroom is identified as something else mistakenly, because it's not that easy, right? Classification. We have a problem of segmentation in computer vision, which is where is it? So given an image, I want to find all the cars, just output the coordinates of those cars. So how do we do it? So let's start by classifying. You remember classification is what is it? By classifying data. So let's say I have this data set of the Jedi versus the Empire of Star Wars. And I want to classify the data, and I have all the names of the characters and all the heights and the mass and the color of the eyes, and are they human? And eventually I want to predict, are they evil or not? So I have this training data, and I already know on that data, is the character evil or not? So one thing that I need to do, as you can see here, is take all the columns that are not numeric and turn them into numeric, right? I have to assign categories, because you can't input the model blue, brown, red. You have to assign categories, and the yes or the no, we also change them to ones and zeros. We do it for the targets as well. Okay, so we take all those features, right, and we do the same thing. We input them into a neuron, and we say, okay, is it evil or not? And it's too difficult to use one single neuron to do that, because it's not that easy of a function like we saw earlier. So for that, we'll have to reinforce the neuron. We have to add another neuron, and then we'll start to think about a neural network. We add another neuron that would get the features. So the first neuron could look at some sort of relations between those features, and the second one can look at some sort of relations. So the first one will look only on the height, mass, and the color of the eyes. The second one will look only on the height and is it human or not. And we can add a third one as well. And each of those neurons will have a value, and eventually we'll put a single neuron in the end that would get those process values and would output, is it evil or not? And now we have a neural network, right? So that's that easy. If you understand how a single neuron works, then a neural network is something that's really easy to understand. So this thing is called a layer. That's a layer of neurons. We have the input layer, we have the output layer, and just to think about it, why do we have only one? Because eventually the question that we're asking is yes or no. Is it evil, yes or no? we will see later that if we have an answer with multiple question with multiple answers, we would have to have more than one output neuron. Okay, so each neuron holds a number, right? So the features are obviously the features numbers: height, mass, color of the eyes, is it human? And then some sort of magic is happening, and the neurons in the middle layer are holding a number, the result of the calculation, and then the last one is outputting a number, and we use something that's called the activation function. So we don't use the actual number that the neuron holds, but we do something that's similar to how neurons in the brain fire, but that's like very generally, it's not that similar. And neurons in the brain, a neuron doesn't always fire, and we won't always fire. We fire only when the value is positive. So that is called the ReLU activation function, which means that if the value is negative, we won't fire. If the value is positive, we will fire. And the reason that we do that, because we want to add non-linearity to our model. If we just keep it like layers of neurons that eventually they do linear combinations, then eventually we can squash our entire neural network to a single or some linear equations, and we want to add this kind of non-linearity. That's why we add this activation function. We have something cool that's called TensorFlow Playground. I advise all of you to play with it, where you can actually see the neural network. You can actually see and play with the connections between the neurons, the number of the neurons, what is the activation function, etc. So now each neuron holds an activated number, and then you can ask, how do I interpret the output? So the output is 12.5, right? So how do I interpret the output? So we'll use something, a function that just takes this value and just smears it on the range of 0 to 1. And if we have a multi-class classification, so it's not just a question of is it evil or not, but we have a multi-class, then we'll also take a function that actually gives like a probabilities. It's called the softmax function that takes the values and does some sort of processing on them, and it gives like the probabilities that every class is correct. So in this example, the probability, or we interpret it as probability of this data represents an evil character is 84%. And the loss that we do is how different are the prediction numbers from expected. So we know that Darth Vader is evil, so 84% is not enough because we want it to be 100%, right? And the accuracy is eventually, if we predicted it as evil or good, what is the percentage of the data or the characters that we classified correctly? Okay, we can easily get into something that's called overfitting. And overfitting, because you can ask, okay, so I'll just put a lot of layers, a lot of neurons, and I have like this super model, super machine learning model that can learn everything. But you have to remember that eventually you have to balance the power of the model and the number of the data points you have, or the size of the data you have, because you can get to overfitting, meaning your model would be too smart. So your model will learn your training data perfectly, and you'll have like 100% accuracy and no loss at all. But when run on the real world data, it would fail because it learned the training data so well. Here you can see that's a problem of image classification. So image classification is when we have the data and we want to classify the data, but our data is not sorted in a table. We don't have numbers that represent the data. We don't have data points, but we have an image. And the image, we want to classify it the same way that we classify our table data. But we'll see that we have some special considerations there, because how do you represent an image? Eventually, you need to put in the input layer, you need to put some sort of number. So how do you represent an image there, right? So in image classification, we have this black box where we output a dog, for example, and where we input a dog, for example, and it outputs yes, right? And we input something that it's not a dog, and it outputs no. And how do we do it? So in supervised learning, we take something that's called, we take labels. So we have all the groups of images that we know they are dogs, and we label them as dogs. and the whole group of things that we know that are not dogs, so we label them as not dogs. And then we just put them and we gave them a label, and you recall that we change our labels from text to numeric because eventually we're dealing with numbers here. So those are called the classes. So I have a class of dog or not dog, and if I have a multi-class, it can be dog, cat, sheep, airplane. And we shuffle them. Why do we shuffle them? Let's take a second to think about it, because if it's not shuffled, and I'm inputting my model, the first dog and the second dog and the third dog and the fourth dog, then my model would learn very quickly that if it outputs yes on everything, it would get 0 loss, right? Because the first one, the second one, the third one, and the fourth one are dogs. And we want to confuse our model, so we shuffle it. Because in the real world, you want to have order in your sets, right? And you have to, of course, shuffle the labels as well. Okay, so we want to input a dog image into our neuron, but how do we do it? How do we input a dog image, right? So one can say, okay, I already know how to build a network that handles features, so I can take this image and I can try to extract the features from it. So I can say, okay, how many eyes the image has, and how many legs, and the ear's length, and does it have fur or not? And then I can build features like I did with the Star Wars character, and then I will input it into the model. But it's not that accurate, right? Because even if a human being is looking at an image, it's really hard for a human being to understand what separates a dog from another animal. Because you can say, okay, number of legs, but then you would have another animal with 4 legs, so you have to separate something else, ear's length, and then you have, I don't know, a fox that's very similar to dog. So it's really hard to train a neural network on images if you do the feature extractions yourself. So you can say, okay, why do we have just one layer? Okay, we can use our neural network, we can use the model, the power that we know, we can use it to extract the features for us. So, we basically want, instead of putting the features into the model, we want to have another layer that's extracting the features for us. And how do we do that? We just input the entire image. And how do we input the entire image? Just remember, image is just pixels, and every pixel has its own value, RGB value or gray value. So it's just pixels. You can take the image and you can flatten it. You can take a 2D image and you can just flatten it. So eventually, if you have a 28 by 28 pixels, you just flatten it, and then you have 784 size vector. And those videos and the videos after that is taken from the great YouTube channel 3 Blue 1 Brown, and it has some sort of those like nice visualizations. So, but that's what we do, right? We take the image and we flatten it and we turn it into a vector, into a list of pixel values. Because eventually it doesn't care, right? The model doesn't care if it's an image or a vector. So we take the image and we flatten it, and then we input that into our model, and we have a layer. That's the job of the layer. It's called the hidden layer. The job is like to extract the features that we can't extract as humans. Okay, and if you want to do it multi-class, we do the same thing like we saw in the tabular data. We just, instead of one output neuron, we put several output neurons, and then we'll have every neuron will run a softmax on that, and it will give us like the probability that the image is a dog or a bird or a cat. So for example, if we know that we have 1,000 classes, 1,000 possible classes, we have 1,000 output neurons, and every neuron will give us the probability that the image relates to them. Okay, so for example, we can do that, right? Instead of having just one output neuron, we'll have like 4 output neurons, and yeah. So it's important to remember that we need to flat everything. And in a multi-class here, we can see that's exactly how it would look. And for example, we have the MVIS dataset. So the MVIS dataset is a toy dataset of handwritten digits that we can use. So we take the digit 5, for example, and we flatten it, and then we input it into the model. And then we see that the neuron that is labeled, the output neuron that is labeled in 5 is giving us the highest probability. So it's saying it's probably 5. So like we see here, we turn into a vector, and then we do this, what it's called a forward passing, right? So I'm turning it into pixels, then I'm moving it forward in my model, and then I'm getting something at the end. I don't know if it's correct or not, but that's the forward passing. After that, I would check if it's correct, I would check my loss function, and then I do something else. I'll do what's called the backpropagation, we'll talk about it in a second. We see that when we do it, something amazing happening, especially like in simple networks and simple images. We see that the layers are actually, if you take the layer and you put it like a 2D again, 2-dimension again, you see that the layers are starting to recognize the features. So here you can see that you have a layer that actually recognizes circles, and a layer that and a neuron that recognizes 2 and 3 and 4. So the layers are actually doing that feature extraction. That's really cool. So the thing that you see here, like the 2 that you see here, is actually a combination of all the 2s in the training dataset that our model saw. So the layer, the neuron knew, the activations of those neurons are for neurons that know to recognize that pattern, which is really nice. Here we can see something that's similar. So we take the 9, and then we have the first layer that's only breaking it into pieces in the image. And that's all the features, the initial features. And the second layer knows to break it into a circle and a line. And eventually it knows to combine everything and say, hey, this is a 9 and not a 6. Okay. Once we do it, we have to calculate the loss. So we have something in our output layer which is not correct, right? Because we haven't trained the model. So we just need to calculate the loss, and then we do something that's called backwards propagation. So we need to update our weights according to that loss. And then we do something that's called gradient descent. You will learn about it in the course. So a gradient descent is just saying, okay, I'm trying to find my lowest loss possible when I'm moving in my weights space. Training is hard, right? And everyone is telling you, okay, you have to learn machine learning, you have to learn AI, you have to learn deep learning, but you see training is really hard. But eventually it works. So eventually you start to do this back propagation, and you do this training progress, and eventually you see that your error is getting down. We spoke about overfitting. So one way to avoid overfitting is just do what we call the dropout. So a dropout is instead of having this really complex model with a lot of neurons, we just randomly remove some of the neurons on every run, on every train. So my model knows not to rely on specific neurons. So it doesn't happen, for example, that if I have training data of cats, so I can have a specific neuron for each image, because when I do a dropout, my model would learn not to rely on specific neurons. So it would just imagine that it would encompass the knowledge of what a cat is according, like on all of its neurons, not just in a single one. So that's how, that's one way to prevent overfitting. It's not enough to flatten an image. Just imagine that you have an image of, I don't know, 4,000 pixels or a 4K image or even video. For that, we're using what's called CNN, a convolution neural network. That's a completely new way to extract features. And it's basically saying instead of flattening, let's just use the 2-dimensional layers. What does it mean in 2-dimensional layers? So like I said, in simple images, in small images, it's really easy, right? Here you can see the CFAR10 dataset, 32 by 32 classification. It's okay. I mean, you can use flattening for that. But when you have 3 channels, and so eventually you have 372 total pixels in an image, just imagine you have satellite images that have like millions of pixels. It's not something that you can flatten and input into a network, and you actually see that the accuracy on, for example, CFAR10 is often not great, right? You can see here that the network, here you can see the activations of the network when run on a cat, on a deer, on a bird. So if you remember when we ran on the MNIST dataset with the numbers, we saw the activation very clearly. It was very clear that the network learned the numbers. Here you can see that the network doesn't really know what it does. And when we look at the confusion metrics, for example, we see that the network has an accuracy of 21% or 39% or 27% predicting predicting the correct class, and it's not what we want. It's not what we want from our network. Okay, so let's get 2D. Let's say that I want to run on two-dimensional layers. And the first question that you're probably asking yourself is why? Why would a two-dimensional layer would be better than a single-dimensional layer? And if you think about an image, if you think about an image of a dog, so how do we recognize dogs? Well, let's say we're looking for ears, okay? So if we have a neuron or a layer that recognizes ears, so an image of a dog, the ears can be anywhere. How do we recognize ears? They can be anywhere in the picture. They can be here or here or here or here. So we want to train something that would know to recognize ears no matter where they are in the picture. And if you flatten the image, then the localization, like the locality, the place of the pixel with its neighbors is very important if you flatten everything. But if you do 2D filters, it doesn't really matter. So we want to have this special something that knows how to identify ear. So the thing to do it is actually to apply a filter, a small 2D filter that's going over the image. And we train the filter as well. We train the weights of the filter as well. But eventually, it would output something. It would output features. But those features would be in a 2D space. Or even if we have several colors or several channels, we can actually train a filter for each channel, then combine those filters together. And that would be the input to the next layer. Okay. And so what is the filter? For example, you can see a very simple filter that only detects edges. So this filter of -1 at the top, 1 at the bottom, and 0, it goes over the image, and you can visualize what it does, right? It takes -1 and then multiply it by -1, and then the bottom one it multiplies in 1. And when you have an edge, it actually outputs, right? When it gets to an edge, it actually outputs the edges. And on the bottom, you can see another filter. So with filters, we can extract features from images that are very specific to images and not just general features. And that's what we want to do. So each layer has multiple filters, and every filter, for example, this is a filter that's doing a diagonals from right to left. This is diagonals from left to right. So each filter is extracting different features, and those features are the input to the next layer, right? So we have several convolutional CNNs, or layers. And then you stack them. And what we see here, that's the architecture of a network called VGG. So you have the image, then you run a filter, and whenever you run a filter, you get like a smaller and smaller images, right? Because imagine that you have a filter of 9 by 9, so you get a smaller output. Because from a box of 3 over 3, sorry, you get only 1 pixel. So you get it smaller and smaller. And something that's nice that we see when we run 2D filters is that even in this case, the layers are learning features that we know how to interpret as humans. So the first layer is learning like the very basic features of what's like here, like patterns, and a more advanced layer is learning like more advanced features. And very advanced layers are learning features that are already starting to be similar to what we would identify as a peacock or a pigeon here. We also have a special filter that's called the max pool, and that's for reduction of the dimensionality, because like we said, we're dealing here with a lot of pixels or a lot of data within one image. So max pooling, just say, okay, take a 2 by 2 square in the image and just do a max on the pixel value and output that. And we can see that even if we run max pool right on the number 7, we get a much smaller image, but we still recognize it's 7. It still keeps like the basic features of those images. And here we can see the activations for level, like we said. So the first level is specializing in lines and colors and very, very basic features. And the second level is much more specialized. And we can actually see that when we train a network on humans, so that the activation of the third layer are all starting to be similar to humans' faces. So how does it look in action? So like we said, you have the image, you have the letter, for example, then you have a filter running over that letter, and it outputs something, right? It outputs the features of that layer. And then you can run a second filter that runs over that letter, and it has another filter. It looks for totally different features, and it outputs the output for those features. And then you pass it through ReLU. Remember, ReLU is a function that lets only positive value pass. So if the red is a negative and the green is a positive, so it lets only the positive, only the green values to pass. And then we do the max pooling. So we take the features that were extracted and we do a max pooling. You remember that we take only the maximum of some sort of square, 2 by 2 or 3 by 3 on the maximum, thus we reducing the dimension of the image. And once we have that, we can already classify it. So we have this, and then we can use a classifier, right? Because we have the features, and you see here the output neurons that actually they get the patterns that the previous layers outputted, and then you can classify it. So basically, most of the time, what you do is, because you have something that's 2D and it's stacked, you just take it and you flatten it. So you turn it into a vector again, okay? Because you have the 2D image, then you have filters, like 2D filters. So you have something that's 2D in your hand, then you flatten it into a vector, and that vector you're passing into a classification layer like we saw in the tabular data, like it's called the fully connected layer, and then you have the classification. So that's an example of an architecture. You have a convolution, right? A convolution filter, then ReLU, convolution, ReLU, then max pooling to reduce the dimensionality of the entire thing, and then again, and in the end you see the FC. That's the fully connected layer, and that's what's doing the actual classification. So just imagine that the last layer, the fully connected layer, it receives features extracted from the images that are so fine that they extracted like in a way that it's really easy for the network to understand from those features, is it a car, is it a truck, is it an airplane, is it a ship? And most of the time, if we look at that layer, we won't understand why those features were selected, but sometimes when you look at that layer, you can see, okay, it's a car because all the images that the network saw has wheels. So it knows how to identify like this wheel thing or this rounded border sort of thing. And we can see this is the confusion matrix when we flatten the image and we didn't use CNN. You can see it's not that good, right? And if we use CNN, you can see that the accuracy is going way better, right? So you have like in the 90s or the 80s, it's pretty amazing. So CNN and it also saves parameter or weights, because instead of taking, for example, a 300 size vector and try running it into fully connected layers, just imagine if you have 2 layers of 3,000 vectors, so you need to have 9 million weights between them, right? Because they are fully connected, so every neuron is connected to 3,000 more. And if you have convolution filters, you don't need to do that. You don't have to have all of those weights. You can have only the weights of the filters, which are usually small, 9 or 16 or 4. You need only to learn those weights in order to, because you run over the image. You don't need to connect to every pixel of the image. Okay, so here's another. You can see that when you take when you take an area in the image, you can actually see the pixel or the neuron after 2 layers. After 1 layer, you can see the neuron that's looking at that. It's called the receptive field. So the red neuron, the red dot, is looking at the green square. And if you have several layers, one after one, you can see that a single neuron or a single weight is looking at a very big receptive field in the image. Okay, let's talk a little bit about tooling. It's important to know what tools we're using to do those kinds of magics. We use we use PyTorch or Keras or TensorFlow. Each would choose their own flavor. But it's really easy to, for example, take Keras, because in Keras, it's really easy to build this kind of network. It just follows your your lines of code, right? So it's really easy to define it. You say, okay, I want sequential, so one after the other, and I want a dense layer of 10. Like I have three input neurons. I have a layer of 10, then I have another layer of 3 output neurons. And that's easy to understand it from the code, right? You just compile the code with the losses and optimizer. It's out of the scope of this lecture. And then you just run fit. And it's really that easy, right? So you have how many features do I have, then how many results, or what's the size of the target layer, of the output layer, sorry. And then you just do it. So you can say that, like I said, you can actually see how you build the network just by using Keras lines or Keras models. Of course, you can run it on GPU because GPU knows how to run it in parallel instead of CPU, which runs serially. Dropout in Keras, it's also very easy. You just add a dropout layer. So you have this, for example, flattened layer, dense layer, dropout layer, and then dense layer. So it's really easy to add it. Convolution, the same. So here you can see the code for what we saw earlier. We have the convolution, max pooling, convolution, max pooling, and you see the activation function here, value. So it's really easy, right? You look at the code and you already visualize how this network looks. Okay, another task that we're dealing with in AI called segmentation. Segmentation is given an image. Where are the things in the image? So for example, this is segmentation that's saying for every pixel, is it a zebra, yes or no? You can have semantic segmentation or object detection. You can have segmentation in bounding boxes that are outputting just the boxes. You can have segmentation plus classification. So how do we do that? We just train a network to classify, is it a cat or is it a dog? And also output numbers, right? Because the model outputs numbers eventually. It doesn't care if it's numbers or classifications. And then you just run a loss on them and you combine the loss, and that's how you train your network. So for example, here you can see how we do it in segmentation. You take a grid on the input, and then you run a class probability for every area. And then, for example, you take the boxes that have the highest class probability for the dog, and you put a bounding box right around that, and you say, okay, this is the dog. The dog is here. And the same for bikes or for cars. And it's really important. Those kind of things are really important in automatic vehicles or in video manipulation or video detection. It's really important. Here you can see something that's like a pose detection. It's actually, so you can see it in real time. Pose detection. That's the same idea, right? You just need the coordinates of the joints to do that. Again, pose detections, and that's actually cool because it knows to detect the joints of the player and the ball, and also the degree of the release, because once you have those numbers, it's just math. Okay, that's another examples of segmentations. Yeah, classification of each pixel in an image, and eventually it takes an image and outputs an image, and we can see later how we use those kinds of models to do other cool things. But yeah, so you have something that's called Mascar CNN, which is a network that knows how to do it. Again, once you can do it on a single image, you can theoretically do it on a video as well. You have this kind of cool thing that knows to color only the balloon, for example. And of course, like I said, you have this video from Coco dataset that knows while driving in real time segment people or cars, and it's really cool actually. It's a really cool video. You can see it. It's 30 minutes, and it's segment and detects in very high accuracy. Okay. Let's talk a little bit about recurrent neural network. So we have one neural network. We can theoretically run it over and over and over and over again on the output of itself or the hidden layers of itself. And then we can analyze sequences. Sequences can be text, audio, video, whatever we want. So if we do this kind of recurrent neural network, for example, we can do one-to-one, which we saw already, is given an image, just output single neuron. Is it a dog? Is it a cat? We can do one-to-many. So given an image, output a sentence, and we can do it, right? If we use several network, we have many-to-one, given a sentence, output a sentiment, for example. Many-to-many is the translation, like we know, and many-to-many can also be given frames of video output a translation. And we have language models. You probably heard about GPT-3 that can generate texts. They are trained on text and can generate text, and they can generate even this kind of mathematical notation that looks like something real, but it's not really. It's not real. It's just gibberish. GPT-3 it has I think 170 billion parameters weights. Just imagine how big it is. Yeah, and here we can see, I'll just go through the example. We can see like a lip reading on a video. Okay, so you have a video and you have a lip reading. A model that gets only the lips and generates the content. Let's talk a little bit about architectures. So architectures of networks. We can see here that the classification error on ImageNet, on this competition of images, how it went down during the years. And after 2014, it actually surpassed human level. So the models after 2014 were better than humans from understanding what they see. So we have this kind of architecture called VGG. I won't go into details, but you can see that the architectures, they can be either like sequential, like the VGG, or GoogleNet, where you output, you shortcut some of the layers to other layers. You have ResNet, where you have like the residual from every layer going to the next layer as well. And we can use that in Keras. We can just, instead of training these huge architectures, and it can take us weeks, we just import ResNet 50, for example, and we just use that to predict, or VGG 16, and we just use that to predict what we want. And we can actually use that, we can replace you remember the last layer, that's the classification layer? We can replace the last classification layer because we just need to extract the features from the images. So for example, if we have a network trained on CFAR, we can use that to train on rockets, for example, because we just take the part of the network that's extracting the features, and then we just replace the classification layer to classify models of rockets, even though the network didn't train on rockets, but the feature extraction, that's what we want. Right. Okay, we see that if we take a network that has like a bottleneck, it actually generates more efficient representation of the data. Autoencoders work on that. So if you take a network and you say, okay, I give you an image and I want you to recreate this image, but I'm limiting the layer in the middle, you can see that in the layer in the middle, the network finds a more efficient representation of the distribution of the data. So for example, here we can see all of the MNIST data casted into the 2D plane by networks. And if we do it not only for images, but also for words, we can have, so for example, let's take a network and let's give the network the challenge to try to recreate or to predict what is the missing word in every sentence. And then we see that the network creates a better representation of the word, a more efficient representation of the words. In that case, that if we take them and we cast the representations on a 2D plane, we see that, for example, the network puts China, Russia, and Japan, and Turkey about the same distance from Beijing, Moscow, Tokyo, and Ankara. It's almost like the network knew that those are capitals of those states. And if, for example, we take Obama to president or speaks to Greece, or that's even nicer. So we take king and queen, the distance between king and queen is the same in the network like the distance between men and woman. So if we take the network representation of queen and we subtract king and we add man, we take king and we subtract man and we add woman, we would get to queen. So the network learns context, even though we didn't tell it the context, just by the correlations that it found in the data and by trying to cast it into a smaller, more efficient space. So here we can see a network that was trained on War and Peace by Leo Tolstoy. So you can actually see the words, how it casted it into, well, it's not War and Peace, but it's still funny to see that. Even in translation, it's nice. So you can see that it casts the words, the English words, about the same distance from each other, like they cast the Spanish words, right? So that's really nice. So it's easy to do translations like that. Okay, let's talk about unsupervised learning. Unsupervised learning is when we try to take a network and we say, okay, I don't know what I'm looking. I mean, I can tell you what the labels are, or I can tell you if the loss is correct or not. You need to learn it yourself. So, for example, those are examples. You take an image and you tell the network, okay, try to recreate the image. I'm giving you only the right side of the image. Try to recreate the left side, or I'm cutting a part of the image. Try to recreate the image, and then the network learns how to do it efficiently. And you can use that kind of a network to identify anomalies, right? Because if you train a network on faces, on human faces, and then you give it a left side of a dog or an orange or a burger, and the right side is not similar to a dog or an orange or a burger, then you know that you have something that is not human there, right? So you can see it's called working on the prediction error in order to identify anomalies. And once you have the network casting, it's called the latent space. So you have the data and you casted it into a lower dimension data. You can actually do operations like we saw. So you can take this Taj Mahal and subtract the representation of day and add this representation of night, and have the network find images of the Taj Mahal at night, even though it doesn't know what the Taj Mahal or night is, right? So you take an airplane, you subtract flying, you add sailing, and you get an image of a boat, even though it doesn't know what a boat is, right? You can use it to do something really cool that's called style transfer, because the different layers in the network extract different data, either on style or on content. So you can take a content image and a style image and just combine them and have like the mixed image. It looks like that. So you have the content image, you have the style image, then you have layers extracting some extracting content, some extracting style, and you measure the loss of your mixed image, right? You input the mixed image and you try to generate something, and you measure the loss, and then you use the gradient to update the input, the image, until you get some sort of combined style, and you have some really nice works on that, and it's really cool. Yeah, you can also do encoding and decoding. So if you encode some original face and then you try to decode something else, then you get this kind of funny stuff, and you have this cool video where you have like an impressionist that's doing impression of people, and the network is outputting the faces of those people, and you can see how similar it looks, right? So you have the impressionist on the left, and then you see how similar the face of the impressionist look. That's what's starting to be called a deep fake those days. You see, it looks like Robert De Niro, even though it's not Robert De Niro, right? That's the impressionist. And you can see here Clint Eastwood, all of a sudden, sorry, not Clint Eastwood. Let's see. The guy from The Fugitive. So, and George Clooney, so that's really nice. Okay, now one last topic is generative networks. So we saw that we can use our model, we can use our networks not only to predict, but also to generate data. So generative networks are something that we input something and we try to generate something else. So we input a sentence, for example, we try to generate an image, or we input horses, and we try to generate zebras, right? And you can do it if you do this, if you play with bottleneck layers and latent spaces, or if you want to do captioning. So here we have, it's another cool video of someone that's going with camera, with a video camera, and it just, the network is generating captions for everything he sees. Right, so it says a motorcycle is parked, black and white photo of something. So it just generates in real time captions of what he sees. And then we take it one step forward to generative adversarial network. So for example, imagine we have a network that its task is to generate something, and we have another network that its task is to decide if that something is fake or not, and they just fight each other. And when they do that, you get better and better accuracy of the generating network, because it needs to like fight a trained classifier. So that's what we do, and then you can generate like really, really convincing fakes, right? We won't go into the architecture. It's really super interesting, really hot topics right now. You probably know this. This person does not exist. Those are images of people that are does not exist. They do not exist. The network just, they pick something from the latent space and they create an image, and you can actually play with that. You can take an image and say, okay, I want less glasses or less of a smile, or more blonde or less blonde, and that's called the style gun. So it's actually taking images and transferring the style from another images. So you can see like in the top, you can see here, you can actually play with that. You can actually tweak the parameters. Yeah, we'll just go, and it can also help to detect fakes, right? Because the pictures that are generated from those models are very, very good. So if you take one of those models and you try to input something real, real target, then you can see that it's not as good, right? So that's how you can detect fakes. Okay, here we some more examples of fakes. Yeah, so I hope it's much clearer now, like this whole space of AI and ML and how does it work. So we talked about neural networks, then we move into CNNs, then latent space and RNNs, recurring neural networks, GANs and text and speech. But that's just the tip of the iceberg. Like Kostya said, there is a lot more to learn, a lot more to understand. We have a lot of things that we can talk. We haven't talked about adversarial or AutoML or reinforcement learning, which is fascinating. Yeah, so we'll skip this. So a lot of more things to explore, and I was Liad, and thank you very much. And like Kostya said, if you have questions, we can talk later. Thank you.